Happy day and welcome everyone. So we are going to be doing the Passing the Gas lab today. Okay, so we know that our goal, our target for this is to kind of figure out like what are the liters per mole and how do they compare? We know that at STP it's 22.4 liters per mole, but what if we're under our own conditions? What should it be? And so hopefully you've had a chance to do some pre-lab calculations and to make your claim to figure out around where that should be, okay? So before I go to a big screen here, I just kind of want to take you through a little bit of what we have going on here. So I have what is called a eudiometer or a gas tube, and this is kind of cool because actually when it looks like this here, let me see if I can enlarge my screen for you here. So when it looks like this, I don't know if you can see this, but the numbers are actually upside down. What? Why are the numbers upside down? Well, the numbers are upside down because when you want to trap a gas, you want to trap it, and so then we would flip it upside down, and now if we looked at it, the numbers look right, okay? And so that's why the numbers are actually flipped on this. So we've got the eudiometer. We also have, I wanted to show you a couple of things. I do have a 3 centimeter piece of magnesium, but I cut this out. And I want to get the exact number of centimeters here. Let me see if I can get you to see this here, but I'm actually at 3.10. I'm at 3.10 on here, so it's a little bit hard to see. Every time I try to do this, I like shift it a little bit, but you're gonna have to trust me on that. Okay, so we actually have 3.10, and that's in centimeters, okay? And then the other thing that we're actually going to need, the reason why I couldn't just weigh this, because I actually need the mass. I don't really want the length. I want the mass of this. But if I put this on a balance, it's only going to give me 1 sig fig. And 1 sig fig isn't enough to do these calculations to be able to get good data. So instead, what I've done is I took a meter of magnesium. So I have this entire huge meter stick that's here. Let's get this so that it's flipped around here. And then I took it from one end to the other and I measured out exactly 1 meter of this magnesium metal. And then I weighed that. And what I got was 1.092 grams for every meter. And so you're going to want to make sure that you write that down. So you should have a data table that's organized. This is just going to be bulleted. But this is the mass per meter of the magnesium, and so this is 1.092 grams per meter. And so I told you that for ours, I actually measured out the length of the magnesium that I cut out, and I cut out a 3.10 centimeter length. Okay, now keep in mind that this is an easy calculation, but you do want to talk to either your group about it or see if you can think about this. Ratios are incredible, but if you know how many grams are in 1 meter, could you figure out how many grams are in 3.1 centimeters? And I'll give you a couple of hints. One, you're going to need to do a little bit of a conversion, okay? So either, my recommendation is to switch your 3.1 centimeters. That's usually easier. And then you can figure out what that would be, how to get that to work out so that you have how many grams it is instead, okay? How many grams this little teeny tiny piece is. And then we would actually be able to use more sig figs in that case, okay? So keep that in mind. All right, temperature of the room we also need. I have a thermometer for that. And so the temperature, these are alcohol based, they're not even mercury, and so sometimes we get a little bit of error with that. But the room temperature, I looked at a few different ones, and we are going to say that this room temperature is 23.0 degrees Celsius. So let's get that down. So the room temp is 23.0 degrees Celsius. Don't forget, you're going to need to be in Kelvin, okay? Do not forget that. All right, and the other thing that we also need is we need the room pressure, okay? Now, if we click, so let's do this real quick here. If we click weather.com, we go to the weather channel, then we don't have a barometer here. You would need mercury open to the environment, and we're not allowed to have mercury here. So if I scroll down and I checked to see, now this is in Fahrenheit, okay, so 25 degrees Celsius, it's actually cold today, all right, so it's below freezing, that's in Fahrenheit. So the temperature that I'm giving you is in Celsius, 23 degrees Celsius, which is in the probably around 71 or 72, I think, if we talk about, if we were looking at Fahrenheit, okay, so we always want to be in Celsius and then switch to Kelvin. It says 30.32 inches, so that's the pressure that we're going to write down. Your teacher may end up telling you that it's a different pressure that you want to use, but for our situation right now, we're going to say that the room pressure, which is the total pressure, because it's going to reach equilibrium, is 30.32 inches. So the pressure of the room pressure, which again, we can call the total pressure P total. So that's what we can call P total. And so we said it is 30.32 inches. That down arrow, by the way, simply means that it is dropping, okay, that the pressure is actually going down, okay. So these are the values that we have so far. If you take a look, we've actually got 4 values, and you only need 5 in this lab. There's only one more thing that we need, okay. Now, one of the other things that that you were told was to get 3, which we're going to use, is going to be a 3 molar hydrochloric acid, and we need about 15 milliliters of it. Okay, now, normally that would go in the data table. The only reason why I'm not putting it in is because it's about. You could write it down with like a squiggly line, but the idea here is you're going to see we're going to end up diluting it anyway. So it's not going to be 15 milliliters that we're reacting, and it's also not going to be 3 molar when we react it. So just keeping these types of things in mind, okay? So I'm going to go back to the lab real quick here just to kind of give you an idea of what we're going to be doing, and then I will show you the lab. So let's click on the dock here. We can see that what it wants to do is we have to cut out the magnesium metal, which we already did, and we're going to fold the ribbon, and we are going to basically create a little bit of a handle with a copper wire. So maybe even while I'm doing this, I can kind of, while I'm reading through this, I can show you here. So I'm just going to kind of fold this magnesium. It's nice because we can see that metals will bend. And so this will bend, and it is, you can see that it's shiny. We know that it's shiny and it's malleable, and so I'm just going to kind of try to fold this a little bit here, just give it a little bit of a fold, and then what I'm going to do is the hydrochloric acid, it does not react with the copper, okay, which makes things really nice. Because what I can do is I can create a little bit of a handle. Hydrochloric acid also doesn't react with plastic, doesn't really react with glass, and so that's why usually when we get it, we'll either get it in a glass bottle or we'll get it in a plastic bottle too. Okay, and it took me a little bit, but I think I've got it. So I've got my little basket created. Again, this is just a piece of copper wire, and it's got the magnesium on the inside of it. Okay, all right, so the next thing I need to do is I need to add this this hydrochloric acid right into this gas tube. People always ask, how is it that I don't spill? And usually I would do this over the sink here, but I always like angle everything, and then it's almost like they're kissing each other. And so I'm just going to drop that right in, and this is about 15 milliliters of the hydrochloric acid. It does burn. It is caustic. You do have to be careful if you get it on your skin or get it on your clothing. We've had students that it might create a little bit of a hole. You might get a little bit of a burn. So what I do is I always like to make sure that my hands stay dry. And so if my hands get wet, then I know to rinse them off. Okay. Now, what it says to do is to fill this all the way to the top with water, okay? So I can see that I have my my acid down at the bottom here, and so now I'm just going to add water. This is going to dilute it, so it isn't 3 molar at all anymore, okay? So I'm adding quite a bit of water to this. So this is no longer 3 molar hydrochloric acid, okay? Now I want to get this to the point where when I add the stopper inside, I don't want any air bubble, okay? So I specifically just want this to be where I know that it's just gas inside of here, and there are little tiny bubbles of air that were trapped when I went to pour the water in, so those are slowly rising. The other nice thing is this has a stopper in it. If this didn't have a stopper, then when I go to do the reaction, the gas is going to build up so much, it would actually kick the stopper out, okay? Or the glass would explode if you had something that was held more tightly than this. So what I'm going to do now is I am going to add the stopper in. Now, nothing's happening right now. I'm going to put the stopper in just to make sure. Actually, I can see it looks good. It looks like this is going to work out great. And so I'm pretty much ready to go here. So since the acid is actually more dense, then the acid should be staying at the bottom. It's not really mixing very much right now. So this is just water on top, which means when I drop this in, I shouldn't really see much of a reaction happen or any of a reaction happen, okay? So I'm just gonna kind of hook this over right over the side of this. Hopefully that will not move when I hook that over the side. And then I'm gonna take my stopper and I'm going to drop my stopper in. Now, I do see that there's a little bit of air when I put my stopper in, so I'm going to add a little touch more water to it. I really want the water kind of like overflowing right over the top. That way I know that there are not going to be any air bubbles or as little air bubbles as possible. Okay, so I'm going to put my stopper in. There we go. And now what I'm going to do is I'm just going to hold the top of this, and then I have this beaker right here. And so let me see if I can aim this down just a touch so that you can see what I'm doing here. And so what I'm going to do is I'm going to invert this, and then we should start to see my reaction happen, okay? So I'm going to flip this over. I don't even need to time it. I'm going to hold the bottom so that nothing comes out. But once I drop this in here, well, now I've reached an equilibrium. And so nothing's really happening, okay? So I did see I kind of lost one air bubble. Sometimes you can have some errors with this where that could happen, okay? But what I really want to see is I'm starting to see a stream. There's a little bit of a cloud. I don't know if you can see this, but there's a little bit of a cloudiness that's coming down this. That's a hydrochloric acid, okay? Now, when the hydrochloric acid comes down here, what I should start seeing, is I should start seeing a reaction with this magnesium. So let's just give this a little bit of a second, and let's see what ends up happening here. What we could do too is, just so that the reason why I have this here, so I may as well start using this, is I can actually put it right in this double burette clamp. That's what the use of that was. So maybe I'll do it this way, and now we can start seeing here what's going on. I can just move this in a little bit closer so that you can get an idea of what's happening. Let's move it even closer. All right, I don't know if you can see this here, but there are definitely bubbles starting to form. Okay, there are definitely bubbles starting to form, and I can see that those bubbles are forming right around that magnesium. And I did not, the stopper is not all the way on the bottom, and the reason for that is otherwise that hole has no use. So there would be nowhere for, if anything needs to get kicked out, then I need somewhere where that volume, where that can change. So let's start taking a look here. Now, I can see bubbles, and let's start seeing what's happening up at the top. Oh, what? So I know when I flip that over, that was full all the way to the top, and now I can see that there's gas that's being created. And we know that since the gas is less dense, then the gas should be rising. So we can see that that gas is rising through the liquid. Well, where's that liquid going? Well, that liquid is actually leaving out of the bottom. Okay, let's see if we can see it. Now, what is it? Well, hopefully you worked out your balanced equation. It is a single displacement reaction. Hopefully you have that. And we know that there's a particular product. Now, we can't see it. Okay, which means it's probably aqueous. It's probably aqueous, which means it's dissolved in water. But if you look at the bottom of the stopper, I don't know if you can see it, but I can see a little teeny tiny like cloud almost, where there is some liquid that must be coming out of there. Ooh, this is going really fast now. Okay, sounds. As far as your qualitative observations go, I'm hearing fizzing. Now, normally if there were class, you wouldn't be able to hear this because there would be so many people chit-chatting in the class, but there's definitely some fizzing going on, okay? So I can see lots of fizzing. This is happening really quickly now. There it is happening, okay? And so that 3.10 centimeter piece of magnesium, let's see what ends up happening with this reaction. Okay, let's take a look up at the top and see what's going on here. Oh, what? We've got more gas that's being filled here. Okay, so this is going to keep on going, and let's come right back, and I will come right back as soon as it looks like all of the bubbles are done, and that, now we say that the reaction doesn't necessarily come to a stop. The reaction eventually comes to equilibrium, okay? So we'll be right back. Okay, it looks really good. It looks like it's all set. If we look closely here, we can see that the magnesium is all gone. I don't see any magnesium anywhere. And then we look up here and whoa, look at all the gas. This from the top, oopsie, there we go. From the top all the way down here. Now, this looks like it's reading about 33 milliliters, but that's not exactly right, okay? So since we collected it over water, we need to make sure that we're at equilibrium, okay? And so I could have really done the reaction in this big battery jar and then I wouldn't have to switch anything up. But because I did it inside of this smaller beaker here, I need to make sure that I line up where my water line is with the water line, okay? And it doesn't matter what container I do this in as long as I'm collecting over water. Here's the idea, okay? You can't see it, but the air pressure is actually what is keeping the water inside of this container, okay? So why isn't the water just leaving? Well, some of it is. That's evaporation. So any of the molecules at the surface that actually can gain enough energy and be able to take off, they will. They'll take off and leave. So the water molecules that are staying inside of here are staying inside of here because those air molecules, the room pressure, that value that we recorded, those are pushing down on there. Well, the water is pushing up against it, okay? So what we're going to do is we're going to take this, and I need to put my finger down back where the hole was again so that it doesn't come out of there, okay? So I'm going to take it, I'm going to grab this, and then I'm going to do the same thing and drop it right, oh no, okay, a little bit of error there, I saw that, okay, but I dropped that inside of there, and what I want to do now is I'm going to use this battery jar. I don't care about the cylinder, I really don't care about that, that's not what I'm looking at, okay, so I'm not looking at the numbers there. What I'm looking at is I'm going to try to line up the volume of the water inside of the tube with the volume of the water here. Why? Well, because then what I'm doing is I'm setting up an equilibrium. What I'm saying is this gas that's inside of here, which, yes, it's whatever the gas is that you figured out from your reaction, okay? But there's also water inside of there. Don't forget, there's water vapor, okay? So since we collected it over water, there's also going to be water vapor that's inside of there. So we're going to need to make sure that we correct for that when we go to calculate what the pressure is, okay? So when I look at this, now I'm going to try to line it up. This isn't very easy, but I know, I kind of want you to get a little bit closer here so that you can see this. So I know that it's going like 32, 33, 34, 35, and before I was pretty much right at the 33 mark, but right now it looks more like 32 points, I'm going to say 32.60. Saying it's about, yep, 32.60. So it is going down. I don't know if you can see the 32, where the 32 is. Sorry, no, not really. I would need to put some white paper behind there. Okay, but the 32, then it goes down to 33, down to 34. So let's write down that it is, this is our last piece of data that we needed, by the way, 32.60 is what we're going with, okay? And then I can just dump this out, so let's write that down. So this is the volume of the gas, but don't forget, this is the volume of the gas, which it's a mixture, okay? So this is the gas plus water vapor. So this is the volume of gas plus the water vapor, okay? Plus, I should say water vapor, water in the gas phase, okay? And so we said 32.60. What unit is that? That's milliliters. This is actually measuring in milliliters, okay? So be careful because we know that anytime we're doing gas laws, we're not in milliliters, we're in liters, so keep that in mind, okay? So using the information that you have, let's kind of take a look back here at what you have left to do here. And so it did say, you know, we had talked about this, I waited 3 minutes and we inverted the tube, and this kind of explains why we're correcting for it in that manner. And so then what you're going to do for your post lab here is you're trying to figure out what the volume of the gas is, pretty easy. what's the mass of your piece of magnesium? So just make sure that you show all of your work for that. So there should be an easy ratio that you're going to use. Then we want to calculate the moles of gas. Now, we're calling this experimental, but some people may debate that it's actually theoretical. And the reason why is the only way that we can actually get moles is by using stoichiometry, okay? By using the amount of magnesium that we started with is being able to calculate and using stoichiometry to figure out the moles of gas, okay? And so then you can figure out what your experimental liter per mole of gas produced is, and then you can calculate your percent yields. Now, your percent yield is not compared to 22.4 liters per mole, okay? So I want to make sure what you're going to do is you're going to take a look at what your theoretical value was, and that's what you should have calculated in 3C and made a statement about in 3D. So that's actually what we're going to be using as our theoretical value when we're doing our percent yields, okay? And so you're going to use, I always say ET phone home, so it's experimental over theoretical is what we're looking at. And then there's a little bit to do with your conclusion, okay? Happy day. I hope you enjoyed this lab, and good luck.